They have like they have the Carol. They don't own the Carol of the Bells. But they have like the best rendition of the Carol of the Bells. Like the one that I think it's in Home Alone. I'm pretty sure.
So it's our last academic meeting. There will be a practical meeting tonight for movies and your presentations on Friday, and then we'll keep hopefully good memories about each other or forget about each other. Commercial. Everyone is invited to join computational chemistry in spring, which is like 467 or 76, and it will be Tuesdays and Thursdays at 11. With it is about 10 times easier course than this one. It's most projects on it. For this course, what do I need from you? Presentations, slides on Thursday night, movies. You can just package everything into the email. And if you want to make favor to the next generation of students, you may attach last version of the working code. If it is like your proprietary software, it's not mandatory, but you can attach it and then it will make life of next generation easier. Good. What is the goal of today's meeting, academic goal? What are we going to get, and who will benefit of it? Who was never exposed to UV visible spectra? Never. I like your readiness. Who is presenting something related to UV visible spectrum? Infrared. Okay, infrared. Well, still something. Yes, and the Isaiah who is absent, his research will be partially related. So the original, this lecture, it will be maybe not highest quality. I didn't spend much time typing in equations, but it will be mostly matching the goals of the overall course. We will make an attempt to bridge your powerful knowledge of physical chemistry and quantum theory with real-world observables. Again, on this short notice, we will, short time limit, we will not reproduce exactly like spectra of this and that molecule, but we'll get through concepts, proof of concept, type of absorption spectra of molecules. And the there is a main feature in the UV visible spectra, especially UV visible spectra of chemical molecules, like not solids and structures, but molecules. Remember when we did rotational vibrational spectra? It was like a little eagle with two wings, right? With each transition corresponding to simultaneous change of vibrational quantum number and rotational quantum number. So there is simultaneous change in the 2 degrees of freedom, 2 types of degrees of freedom. The same for, and rotational spectra are in more very infrared, like far infrared, and near infrared, UV and visible. There are simultaneous transitions of electronic degrees of freedom and vibrational. Therefore, even if you are looking only on 2 electronic states, the spectra of molecules are very different from spectra of isolated atoms. Instead of lines, there will be bands, and sometimes it will be like fingers with some substructure, because each electronic level has several vibrational sublevels. If you feel comfortable with this idea, you're done, or you can like wake up when I will be showing it and look where it comes from. If you're not comfortable with this idea, you can protest right now. I do not like continuous spectra of molecules. I'm against that. No? Last time we made a dictionary between quantum states of two level system, which is spin 1/2, which is called also in NMR a W, right? It doesn't surprise you. Up and down, two states, W degenerate, W. And there are operators. And here what the connection between spin, expectation values, and magnetization. And we didn't went to this, but if you let spin in magnetic field, it will freely rotate X and Y projections, which is main cornerstone of the NMR experiment. The stronger the magnetic field, the quicker will be the rotation of the spin. So if everything will go successfully, you'll see this ugly drawing once again. So what do you see and how you interpret it? Any ideas? Well, if there will be 5 fingers, it can be like palm of a human. If there are more fingers, maybe it's from extraterrestrial palm. So this shape is typically what one would see if you take absorption or emission spectra of molecules with like a couple dozen of atoms. So instead of lines, there will be a resolved structure. It differs from molecule to molecule with the offsets in these fingers between overall shape of this substructure, but and sometimes they are not resolved and go continuously. It depends on the temperature, but it is relatively standard way how UV visible spectra work like. So the lowest transition corresponds to no change in vibrational quantum number, and here it means that there are simultaneous change of both electronic and vibrational quantum number. Make sense? Who is Stokes? Who has never heard about Stokes? Never. Okay. Whoever heard about Stokes shift? What is it?
I don't remember.
But you've heard about it, but not.
Yeah, I think it was in CHEM2.
Okay. So if you have the same molecule and you record its absorption and emission spectra, they will, and just overlay them together, they will not coincide. Like if you would look on the atomic spectrum, the energies at which transitions occur do coincide for absorption and emission because it is the same electronic levels, right? But for chemical molecules, emission happens at lower energy than absorption. It generally happens always. And even with more details, there are some features like if this is red, this is like rainbow going to the blue, and this is absorption spectrum. For the same molecule, let's assume this is not 0, but some other number. So if this gray thing is absorption, then emission will have a shape, the same shape, but it will look like mirror reflection. Emission, absorption, and the difference in the maximal is Put stocks store. Well, right now we are speaking phenomenologically without equations, but if you get exposed to any spectroscopy, maybe in PChem lab next semester, if you're taking it, you'll see something like this. If the spectrophotometer function well. But you may see it in research labs or in the literature. So, what is a molecule? From the height of your today education.
Collection of atoms held together by chemical bond.
Yes, but you do not need to study in college to say this. It's like high school collection of atoms with chemical bonds. From your like high orbit of multiple knowledge, can you add something more to the definition of a molecule? Anyone? Well, atoms are ions, nuclei, and electrons. Right? And when atoms connect into a molecule, what happens? These electrons.
Become intertwined between both of them.
Yes, the electrons are shared. Right? So instead of orbiting around single atom, they become, how to say, shared. They do not belong to a single atom. Right? So it is a collection of positively charged nuclei and negatively charged electrons. And electrons are quantum particles that just are distributed in space through wave functions, and one typically characterizes them by energies rather than radii or places where they are, because they move in quick. Good? What about ions? Again, from the position of your today's knowledge about harmonic oscillator.
An atom that either has too many electrons or too few electrons.
Nuclei they are not nailed down to the wall. They experience attractive and repulsive interaction. They have optimal interatomic distance corresponding to chemical bond, but they are allowed to move, to come closer or to move apart from each other, to perform some oscillations, right? You don't object. So electrons are clouds, nuclei are just like balls on springs. Good? So this is more. Now, what is the connection between electronic and nuclear degrees of freedom? Would the interatomic forces stay the same if you change electronic configuration, if you ionize molecule or photoexcite it or reduce it? Just from the verbalization of a question, you may come to the idea that maybe not, right? So the forces between nuclei are determined by repulsion of this positive force and also attraction of the electrons around one nuclei to another nuclei, some additional electronic forces because of shared electrons. So the shape of electronic orbitals in this shared arrangement affect how strong or how weak nuclei attract or repel. Okay? So if you excite molecule from ground to excited state, forces between nuclei change. And the first consequence of this thing is that the equilibrium position is likely expected to change. So if G doesn't stand for genome or for congenium. It stands for ground. Ground excited. If nuclei do not move, if you freeze them, the transition from ground to excited electronic state is just vertical line. But if we take into account chance that nuclei can move, then one represents ground state by potential surface, which we were describing as little harmonic oscillator if we are close to this equilibrium, if there is no external perturbations. But if we go to the excited state, the equilibrium position can be offset away from this equilibrium. And potential curve can have different steepness. And this picture of the offset potential energy surfaces is fundamental, general. It applies to any molecule. The parameters are different. The area of definition, like it will be one-dimensional only for diatomic. If it is many atoms, it will be like a huge number of interatomic distances. Sometimes one can reduce many dimensions into one, but it is a challenging task. But generally, for each electronic state, there are different potential energy surfaces. Okay? Good. Who cares why do we need it? Why do we need spectroscopy? Why do I need spectroscopy? Why do you need spectroscopy? What is spectroscopy?
Allows you to characterize molecules or whatever you have in your sample.
Characterize means first thing, identify. For just if you cannot see atomic structure by human eyes, you need to identify which molecule it is. And if you cannot smell or look, taste it, it's better to characterize by a spectroscopy. Right? So each molecule has its own spectra, and often by looking on a spectrum, one can identify which molecule it is. So this is practical task for actual spectroscopy. For us here, we can go in more natural way. Suppose that we know atomic structure, how can we predict the spectrum? Right? And if this bridge, if this connection, relation between structure and the spectra is known, then anyone can use this connection. Right? We will not be able to cover this huge material in the remaining half an hour, but it is general direction why spectroscopy is needed. What else? Spectroscopy of molecules, really visible. Shapes of the spectral lines. So the mini task for today is how the parameters of these potential surfaces, curvatures and offset in position and in energy determine the shape of the spectrum. Can we find some trends generally and then apply them to practical examples? Good? What is spectroscopy? I know I look like a little crazy, we just discussed it, but we discussed what are the benefits of spectroscopy. But what is spectroscopy? Can we define it?
Using some type of wavelength of light in order to determine an absorption or transmission of an
Absolutely correct. It is even too specific. We can say more general. Probing properties of molecule by perturbing it with electromagnetic radiation, or exploring the response of a molecule to electromagnetic radiation. And then the response your input parameters of your probe can be like wavelengths, and the response can be intensity of absorption. Probing piece of matter, molecule, with electromagnetic radiation, exploring response to radiation. So what is electromagnetic radiation?
Light,
What is light?
photons.
It's too smart for me. If I'm illiterate and I'm living 150 years ago, what is light for me? Well, like there is a duality of particles and waves. Photons are particles. What is the other side of the picture? So what is electromagnetic radiation? You all know it. Maybe I'm asking it in a odd way. I need to request help from an expert. I know that Michael can answer this question without opening the notes. What is the wave? Yeah. Good. So what is oscillating in electromagnetic wave? That's a tough question. Who took any you don't need to take college physics. You had physics in high school. Who hadn't who never exposed to physics in high school?
I went to college.
Okay. But then what is oscillating in electromagnetic wave? Michael already did his share. He showed like visual leadership, and we all need just to provide the remaining details.
A beam of light that moves as a wave.
What is beam of light? Beam is ray, but oscillate. What is oscillating there? Wave means something is oscillating. In the past, we considered waves of probability for electrons, right? Before we were discussing like waves on the surface of a lake. But what is oscillating if light is shining on you?
Energy.
Charges. Photons.
UV, visible, infrared, it is a frequency of oscillations. How dense or how sparse are the fringes? But what is oscillating? Which physical quantity? Which observable? We should start with. I should reverse the order of lectures. Make this one first, and maybe next year make an experiment. Count. Yes, perfect. Anyone objects to Bill? No. Okay. So what is electric field?
Separation of positive and negative charges.
Well, one can develop some ideas just looking on the screen, right?
Yeah.
Well, electric field is the force acting on unit charge. Is the reason why charges are moving. So if in vacuum you have electron without momentum and it starts moving, it means electric field did act on it. Electric field appears between contacts of a battery. anywhere where there is difference of voltage, there is also the electric field. And electric field may exist not between like bias of a battery, but just standalone in the space. If it oscillates and propagates, it will be like, okay? We will be departing from each other very, very soon, but you may want to, on the background, think about it and become ready to answer it, maybe for some other instances, because it's like really, really basic things, which not even for professional scientists, but for like general public. Electromagnetic radiation oscillating electric fields, propagating itself. Electric and magnetic, they are orthogonal in space. Now, why electromagnetic field probes molecules? Why it perturbs? It's not a tricky question. It's just very simple logic. Definition: electric field is something that makes charges to move.
Molecules or charges.
Yes, molecules are charges, right? Positive and negative. So positive will go one way, negative in another. As soon as you have electric field, molecules will move. Sometimes, if molecule is neutral and non-polar, it will be the perturbation by electric field will be much less. But still, they can polarize slightly and get response to electric field. And there are so many electrons, so many ions. How can we count the interaction between matter and light? Approximately. Right? So the simplest thing that would, like if it would be charged molecule, it will just start moving towards field, forwards and backwards. But if it is a neutral molecule, net charge is zero. But there are positive and negative charges. They can be offset in space. And how do you call two charges which are offset in space and separated by some distance?
Electric field?
No, electric field is like big thing that affects your molecule.
Potential?
Plus and minus and distance between them. We are having true physical chemistry today. Well, if it rotates. But rigid rotor can be neutral. By the way, for gauge, if your rigid rotor doesn't have charges, it will not respond to magnetic field. The reason why it responds to magnetic field because there are positive and negative charge, and moving charge creates magnetic dipole and responds to magnetic field.
Is that an ion? Or, sorry, an atom?
How do you call this game when you put empty boxes and guess the word? By wow? Huh?
Wheel of Fortune? Hangman?
Probably, like TV show. It's a good idea. I don't have time to prepare it right now, but next year.
Combine E.
Dipole?
Perfect.
Oh.
Do not tell me that Bill was the first one who opened your eyes and you never heard this word. Dipole. So electric dipole. So if the electric field is applied and you have a dipole, how would the dipole respond to electric field? Like if there is an isolated charge will just move towards the field or against the field.
So it'll rotate to align with the
Yes.
field.
Yes. If the angle between dipole and electric field is zero, it will just stay where it is. If it is non-zero, the dipole will rotate. Now, the main idea you did hear what Alex the electric field will rotate dipole, which means there will be some torque, some analog of force that will make rotate it. If it is not aligned, it will be energetically unfavorable. If it is aligned along field, it will be energetically favorable. Right? What does it mean? The energy of your system, field plus dipole, depends on orientation, right? There is a specific energy associated with angle of dipole. There is a specific energy of interaction between dipole and electric field. This is if someone needs to be on schedule and go, you leave, but I will continue even if everyone is leaving, because it is important things, and at least for the recording. Whew. I seem to be here at about 5 minutes after the start. There are much more complicated things. This is just background without which we can go forward. Okay. There is an energy associated with interaction between dipole and electric field, which is scalar product of electric field vector times dipole. If angle is 0, it is negative and minimum. If it is at like 90 degrees, it will be bigger. If it is opposite to the field, it will be maximum. Why we care about energy? Because you are physical chemists and quantum theorists, right? And you always seek an opportunity to write down a Hamiltonian for any system. And Hamiltonian is energy. So if you want to describe interaction of light and matter, you need to add another term into Hamiltonian. And this term will be a product of your electric field times dipole. Good? So electric field oscillates, interaction is product, and dipole, if there are many ions, positive ions and negative electrons, is summation of them. As quantum theorists, you may know or you may guess that that molecule can be characterized by its wave function. There is a probability distribution for each position of each electron and each position of each nuclei. So it is like thousand dimensional wave function. And one can factorize it on part that depends on electronic state and part that depends on nuclear state. So the main, I wouldn't say theorem, but main statement of the spectroscopy is that the intensity, the ability of a molecule to go from one state into another state will be equal to matrix element of this initial and final state with operator of interaction. And since electric field doesn't depend on what molecule is doing, we can pull it out of brackets. So which means that ability of molecule to interact with light will depend on the matrix element of dipole. And dipole is just position times charge. So we spend so much time in the particle in the box trying to find expectation values of position. So finally we see why it is needed. So if you have a molecule, you have wave functions, then as soon as you are able to find expectation value or matrix element of position operator, you immediately become able to describe interaction of this molecule with light. Matrix element of position operator is critical for spectroscopy. Okay. And as soon as you do have matrix element, you are opening Wikipedia and looking for Fermi's golden rule. Who have ever heard about it? So I will be the first. If there are two quantum states, if there is an interaction that connect them, if there is a matrix element, and there is a density of states for this initial and final, then the rate of transition from state 1 to state 2 will be matrix element of transition squared times density of states. So Enrico Fermi made first nuclear reactor, got some prizes, and this rule helped him to. When we do spectroscopy, we use the same Fermi golden rule. The interaction will be matrix element of dipole. The density of states will be just density of initial and final states. Whew. So, it's all correct, but no time. The wave function of a molecule is a product of electronic part and nuclear part. So initials, we can solve time-independent Schrödinger equation for both electronic and nuclear parts and find eigenstates. This is much more complicated than anything we did before. It's even in the simplest case, it will never be one-dimensional. It will be three-dimensional for electron in simplest and one-dimensional for nuclei in simplest. But then, so notation. The letter phi stands for electronic. Index M stands for all quantum numbers related to electronic state. Letter chi, I'm not Greek, I don't know how to pronounce it, but that looks like X, but it is a Greek letter, stands for
Chi.
Thank you. Chi.
Some of us are in Greek, but
so chi stands for nuclear wave function, and M stands for quantum number, how many oscillations. So these two indices and the energy associated with M and N is initial state of a molecule before it got excited, and then another pair of states, phi sub n and chi sub n, and capital, is final state. So both electronic quantum number and vibrational quantum number are changing. So the Fermi golden rule is here. So this F sub all indices is just V M M N N matrix element of the dipole interaction square. And some people call it, you know it, oscillator strength. Oscillator strength. Oscillator strength. So dipole interaction matrix element squared is oscillator strength. It's how easy light can promote the system from one state to another one. Here is the density of states, which is density of excitations. It is a resonance condition. Excitation can happen if the energy of initial state and energy of final state are in resonance with exciting light. Without resonance condition, absorption and emission is possible, but it will be so much weaker, like by 10 orders of magnitude, so we can forget about it. So absorption at frequency omega will happen if resonance condition is matched and if the matrix element is non-zero. Oscillator strength which is matrix element of dipole square. Now, I do want to show fingers, not my fingers, fingers for this absorption spectrum. For simplicity, I even can assume that, well, forgive me, let's factor these two things. For resonance conditions, we can assume that energy of ground and excited states, electronic ground and excited states, are fixed. We have only two states. And then we do not speak about M and N anymore. But for vibrational states, we can assume that both potential curves are harmonic oscillators. And energies of harmonic oscillators are h bar omega frequency, 1/2 plus quantum number. Frequency, 1/2 plus quantum number. But quantum numbers for initial and final states can be different. Okay? Then the energy which will enter into the resonance condition will be electronic energy difference, EL for electronic, and then vibrational energy difference. If the frequencies are the same, it will be just difference of nuclear vibrational quantum numbers times frequency. So we are done with this part of Fermi golden rule for absorption. Now we need to deal with this oscillator strength. So we do have operator, electronic initial, electronic final, nuclear initial, nuclear final. The ions, R capital, move so slower than the operator of dipole mostly affects only electronic degrees of freedom. Therefore, this expression for matrix element is partitioned onto the matrix element of position in of electronic position times overlap of nuclear wave functions. So this will be just a number. Matrix element of position operator. This is transition dipole, which enters into oscillator strings, and Ben may have practiced it in his research. It is what computational codes are doing, and what those who will take computational class will do. Just assess this matrix element through specific code. This part, associated with quantized nuclear vibration, is called Frank-Condon factor, which means if this nuclear wave functions coincide and overlap, it will be most efficient transition. If they are offset, it will suppress absorption and emission. So just overlap of nuclear wave functions for initial and final state substantially modulate intensity of absorption or emission. And it is called FCF, Frank-Condon factors. Good. And here is the illustration. Ground, excited, set of different quantized state of quantum oscillator. From ground state, electronic ground state, nuclear, one can go to ground nuclear, first excited nuclear, second excited nuclear. And they will have different transition energies and different intensities. So how to find these things? I do not have a right to keep you. If you need to go somewhere, I'm not keeping you, but I will tell it at least for the camera. Whew. So another important thing. For the excited state parabola, which is offset by position, this ground state parabola for ground electronic state looks like an offset Gaussian. Looks like a coherent state that we also covered in harmonic oscillator. And one of the last lectures in harmonic oscillator chapter was how to express coherent state in terms of ground state. So it's ground state wave functions times parameter of eigenvalue of annihilation operator in power m divides square root of m factorial, and then this normalization factor. So if we find out this alpha parameter, which is just offset of this potentials in position times some factor, we can immediately express excited different states in the same basis. And we can immediately assess within like 2 minutes the values of Frank-Condon factor. So here is the connection between offset of position minima converted into this parameter alpha, frequency, mass, h bar. And then the Frank-Condon factor that you enter into the transition for this Fermi-Golden rule will be expressed in terms of this coherent state expansion. So in fact, we will need just to plug some values and take factorial and this alpha parameter into power m. Yes. So example, I am about to finish in 3 minutes. Suppose we have oscillating carbon, maybe some crazy molecule of carbon diatomics, which is not stable but in vacuum. Then typically the mass will be 12th mass of product, about 24,000. In Ben's work, research you put mass of bromine, which will be over 100. Frequency you can put like 0.1 electron, which is just typical. And then this, we can set up offset some arbitrary number like 0.28 atomic units, which will be like 0.15 of angstrom. And then this parameter alpha, if you plug in all values, will be 2. So Frank-Condon factors for numbers 0, 1, 2, 3, and so forth will be plugging in number 0, 1, 2, 3 into this expression. If we carefully do it, the numbers here will show 2 trends. So it is a function of number n. First, when m is small, the function will grow because it is alpha to the power 2m. So it will, the maximum will be about 10. But then, with the larger values of m, it will start to decrease because m factorial is stronger than power function. Let's go back. So those are Frank-Condon factors that modulates intensity of spectral transition. Those we can plug in delta E plus energy difference, h bar omega, 2 h bar omega, 3 h bar omega. And now when we have this table, we can plug it into this expression. So offset 0 h bar omega, 1 h bar omega, 2 h bar omega. Here is the electronic transition, and here is that simultaneous electronic and vibration. Here we do plug intensities, which first grow and then decrease. And then each individual transition is wrapped up with some non-zero bits, the same way as we did for density of states. Right? And then you get this extraterrestrial power. So we did start it with the concept that molecule is collection of electronic wave functions, distributed over several ions, and interatomic distances depend on electronic state. Then we applied light to matter interaction in form of dipole operator, used Fermi-Golden rule, and obtained the result that transitions, response of a molecule to electric field at frequencies, at different frequencies, will have different intensities. And this profile does depend on the offset of the minima of potential energy surfaces. If there is no offset, it will be on the first line. Larger offset, the swing will be protruding further. So, this is the best thing one can do in physical chemistry in 4 months. Congratulations with completion. Looking forward to see you tonight if you need help. If you do not need help and can generate videos, I'm just looking for your videos, presentations, and to see you on Friday.
Can you have that on Monday?
Free slides.
I changed mine. I didn't think it's spicy. I went back and
Do you see any possible adjustments to your food based on this material?
I thought I was, but then I always try that class with my mom, with my girlfriend, and she did class from like
Just keep
11
thinking.
to 2 that I forgot about.
Yeah, if you present slightly different than what is written, it's